This video is made for the Core 1 competition organized by Kurt Jaimangal from Theories of Everything and is sponsored by Alpona Publication.
What if, instead of our usual 0 through 9, our alphabet was made of primes? What would that even look like? How would it change how we write a number like, say, 45?
How do we define a number by taking a base? So here, if n is a number, dk would be the value of the kth position. So dk can be a number between 1 and 9, and b is the chosen base, and b to the power k. K is the value of the position itself. The position is the first position, so base to the power 1, and then dk is what number is in the first position. And then we sum up the multiplication of these values of the position and the base to the power that position, sum up all of them, and then we get a number. That's how each of the numbers are constructed.
We're going to take the number 13 and break it down.
So how do we exactly write 13 in the base of 10? So what we take 3. 3 is in the 0th position, so we are writing in the decimal base in the base of 10. So we put 10 to the power 0, the position is 0, and then in the 0th position, what number do we have? We have 3, and we add it up with the base to the power 1, the first position. What's in the first position? It's 1. So then we add them up, so 3 times 10, 10 to the power 0 is 1, it's 3, and 10 plus 3 is 13. That's how we write a decimal number. Now how do we write a binary number into a decimal? The representation of 13 in binary is 1101. It's in the base 2, that's why it's binary 0 or 1. We again do the same thing. We take the position as starting from 0. So there is our base. So base to the power, the position is 0, and the value of the position 0 is 1. And the value of the position 1 is 0. Value of position 2 is 1. And we multiply all this and we add them together, so we basically get 2 cube is 8, then we get 4, and then we get 1, and this one is like 0, so we get 13 back. So that's how like we are converting the binary back into the decimal.
For decimal, it's all about powers of 10. For binary, powers of 2. The position of each digit tells you exactly which power to use. This is the prime sum representation, or PSR.
Now we're going to transform all the numbers into the prime sum representation. So what is this prime sum representation? It's like a dynamic system. So in normal case, like we have like 10, 2, octal, hexadecimal. In prime sum representation, we would take the base as a prime base, and we will work with it, and why it's dynamic we will see in a moment. So like this base is fixed for all the other systems, where like 10 is always fixed as a base, but in the prime sum the base can change. What do we mean by that? We'll see in the next step. So first we check this example here. Like we take a number n equal 13, so we will transform 13 into the prime base. What is the largest prime less than 13? So first we find the largest prime number less than 13. Now we consider that 13 is in the base of 11. What does it really mean? All the prime numbers up to 11 are in the base of 11. So 2, 3, 5, 7, 11, these are all in the base of 11 according to their position, the same way we studied the positions before. We would try to sum up all this and get 13 back. We would always try to find the largest number we can add to get back to 13. So the largest number that's closer to 13 is 11 itself. So we take 11, 11 is on, so we have 1 for 11. And then we try to add 7. We can't add 7. It would be higher than 13. We're not going to reach 13. We try to add 5, then we try to add 3, and all these are not gonna work. So when we add 2 with 11, we get 13 back. What happens is we get a set of numbers 1, 0, 0, 0, 1 that becomes the prime sum representation of 13. So now 13 has been converted from decimal to the PSR system.
You've got binary, a system with a fixed set of rules, all based on powers of 2, and on the other, something totally different, representing 45 as just a sum of primes. PSR is dynamic. Instead of one fixed set of building blocks for all numbers, it creates a brand new custom set of prime numbers for every single number you want to represent. It's like every number gets its own custom-built alphabet.
So what's the general form of this PSR system? Pi are the prime numbers for the highest prime base, and Ci are the coefficients for the base, and we also have another term, remainder R. Prime numbers, it starts from 2, so there can be a remainder 1 or remainder 0. If remainder is 0, that's a perfect sum. If remainder is 1, that's still a sum, but that's imperfect. For the remainder, we get 0 if all the prime numbers sum up to n, and if it doesn't, we get a 1 remainder always. R is also between 1 or 0. For all the numbers greater than 3, there would be either no remainder or there would be 1 as a remainder. Now we're going to check an imperfect case where we have remainder as 1. So for the number 14, if we try to represent into the prime base, 13 is the largest prime number, closer to 14, and so 14 is in the base of 13, and the set of all the prime numbers in the base of 13 is 13, 11, 7, 5, 3 and 2. Now we do our greedy search, so we check 13 is less than 14, include 13, remainder is 1, 1 is less than 11, exclude 11, 1 is less than 7, exclude 7, 1 is less than 5, we exclude. So the remainder we have is less than all the numbers. We cannot subtract any of the numbers. So what we have to do, like we have to keep the remainder until the end. So if the largest number plus the remainder makes out the number n. So what becomes of all these others numbers in the set? All of them become 0. So all the other digits become 0 and we have only 13.
The number n is just a sum of different primes, and just think of those C things as on-off switches. If a C is 1, you turn that prime on and add it to the sum. If it's 0, you leave it off. The final number is just the string of all those on-off switches.
One thing we noticed before that, like as the number grows, we need like more and more prime number. So we have like for 13, we have 5 prime numbers, and in the other case for 20, we have like 8 prime numbers. So the amount of these zeros and ones, the coefficients we are taking, will change with every iteration. We go up a number, this is gonna change. So it's like it's not same as like a 8-bit code or a 4-bit code or a fixed 6-bit code. Like the fun part is it's both dynamic and at the same time is static. So what's the static part? The static part is how long is it static for. So in between a range of 2 different prime numbers, this is gonna be static. There can be 5 prime numbers, 5 coefficients for 2 specific numbers, or there can be like 8 prime numbers, 8 coefficients for 3 specific numbers. More generally, if I would say, between every prime gap, these bits are static. With the changing prime gaps, they are becoming dynamic. So it has both its static property or dynamic property, and we can utilize both of these static and dynamic properties to encode our data.
What if we did the complete opposite? What if we built a system with a totally rigid, unchangeable set of primes? Perfect prime power summation, or PPPS for short.
We have the proper understanding of how we can change a number from one base to another base and encode our information in there. So now what we're going to do is we're going to utilize a fixed prime system where we will choose our prime numbers from before, and we will only keep the perfect sums. So this part is really important because only the numbers we will represent using these fixed primes. If one of the numbers doesn't have a perfect sum, we are not gonna take it for this fixed set of numbers. From before, we choose 3 prime numbers, like we have chosen 2, 3 and 5. They could be any 3 prime numbers, but they will be fixed. And then they have got this power a, b and c. So now what we do, we try to get a number n depending on these powers a, b and c. So we try to reach to n. So n is a number that we're going to represent in this base. We will have to figure out the powers a, b and c using the algorithm. So we choose, suppose 2 to the power 1 and 3 to the power 0 and to the power 3, and we will see if we can get n or not. If we get n, what happens is 3, 0, 1 would be the fixed prime base for the perfect sum.
With PPPS, the rules are totally locked in. The prime bases are always 5, 3, and 2. That never changes. So the game here isn't picking the primes, it's finding the perfect combination of exponents, a, b, and c, that adds up exactly to your number, which means you pretty much have to try everything until you find a match or run out of option.
If n is equal 48 and our prime numbers are fixed 5, 3, and 2, then what n would be in the basis of the perfect sum? How do we find it? We find values for a, b, and c. So we take the largest prime number and we try to figure out its power first. So 5 to the power 1, 3 to 3 cube, and 2 to the power 4 would give us 48. What 48 is in the base of perfect sum is 134. So we are encoding the information of 48 into 134 using this fixed prime representation. How the algorithm basically iterates is log base of 5 of 48, and we get the number 2, we floor it, and then we try to plug in 2, and we are getting 25. Our remainder is then 23 if we negate it from 48. Then we try to check if 23 can be represented as 3 to the power b plus 2 to the power c. If we don't find any perfect sum, we go back and we take a as 1. So now like 5 to the power 1 is 5, remainder is 43. Then we again try to find b and c. It's a tedious algorithm where we have to like iterate multiple times back and forth and check which number we can take to the power of the largest prime number, then is smaller than that, then is smaller than that, to reach our goal. But this taking the fifth log, 5 base log of 48 would tell us where do we start from. Here is an example when perfect sum is not going to work for some given numbers, like n equal 49. So we are trying to encode 49 into the base of perfect sum. We are trying to take the same fixed set of numbers 4, 5, 3 and their powers a, b, c, and we are doing the same thing. We will start from 2 and then we will try to reach 49, but there is like no possible way to reach 49 using this method, no matter which power we choose. If we sum them up, it's not gonna sum up to 49, it will sum up to 48. So this number 49 cannot be represented in the base of perfect sum using these fixed values that we have chosen. So there are more examples here, so we can like try other examples from the ASCII chart and we get the same result. So this is an exciting thing that we don't have some of the values from our ASCII chart.
PSR uses that quick, biggest first, greedy method with a custom-made set of primes for every number, and it always finds an answer. PPPS, on the other hand, uses a slow, exhaustive search with a fixed set of prime powers, and sometimes it just fails.
We cannot encode into 5, 3, and 2. But there is the fun thing that we can change these fixed values. So now we have taken 5, 3, 2, but we can change and take another combination like 5, 3, 7. And all the combinations we can take, we can still like write 49 in one of the fixed bases, but not this one. So here we can encode some selective amount of data with a fixed base. Then we can encode a second data with another fixed set of prime numbers. We will encode this data into the other fixed set which is compatible to it. So it is a kind of multi-layered structure. It doesn't end here. Two things to look forward to. We can do more research on this field, like we can change these fixed primes, which combination of these fixed prime would generate which set of numbers, and how are they gonna span the whole set of natural numbers. That's one question that we can research. In this term we have got this remainder, and it's really special because this remainder is sometimes 0 and sometimes 1. So it itself is encoding some information about our progression from one number to another number. So like if we check the information of these like ones and 0 across the number line, when did we get another 1, when did we get another 0, what's the sequence of getting 1 and 0 based on n. So for some n we get 1, for some n we get rs0, but they themselves has an index. What remainder are we getting if we take the first number? These remainders themselves are constructing a structure and also encoding some information about the prime gaps as we move through the set of all the natural numbers. So this is more interesting to me, but this is another question to be asked, and we can move forward from here to do more research. There is more stuff not discussed in this video as it is supposed to be kept practical with utilizing all the available tools, but there would be a new book on prime numbers where many more stuffs are gonna be discussed. You can check this newly released book from Alpuna publication. Holding this book feels like holding the entire universe in the palm of your hand.